Okay, in this example I want to show you how you can calculate 25 to the power 583 modulo 279. As you can imagine, these are really big numbers. If you really would want to calculate 25 to the power 583, you would get such a huge number. It would be almost impossible to handle. But yeah, luckily for us, it becomes a lot easier if you are working modulo a certain number, because then the values that you have to work with will not become that big as without the modulus. What's a general strategy for calculating such a value? Well, first of all, we know the Euler theorem, and if possible we want to apply that first, because if we apply that, the numbers will become considerably smaller, so it will be much easier to work with. Why can we use not always use Euler theorem? Because it has a few requirements. First of all, in the Euler theorem itself, it says that the greatest common divisor of the lower number here, 25, and the modulo, that greatest common divisor has to be 1. So we have to check that first. If not, Euler can simply not be used. But also, if the exponent here, if it is if it is smaller than the phi of the modular number, then Euler theorem can also not be used, because it does not give us any advantage then. So the theorem applies, but it does not give us an advantage in calculating this number. So we have to check these two things, and if so, we can apply Euler and reduce the numbers significantly. If not, if one of these two requirements is not met, then we can use the technique of modular exponentiation, which always works. So yeah, you could solve any problem of this form using this modular exponentiation, but it's really a lot more work. So that's why we want to try to use the Euler theorem first, and then the modular exponentiation. In this case, we have to check whether the greatest common divisor of 29 and 279 is 1 using Euclid. We do that with a table as before, so yeah, you know how it works. We take the biggest number of the two, 279, and check how often we can subtract 25. We can do that 11 times, and then the remainder is 4. So then we consider the values 25 and 4. How often can we subtract 4 from 25? Well, 6 times, remainder is 1. So we continue with the values 4 and 1. How often can we subtract 1 from 4? We can do that 4 times, remainder is 0. 0 is the sign that we can stop. Greatest common divisor is 1. That's good, because that means we can apply the Euclid theorem. First of all, when you want to apply Euclid, you have to calculate the phi of 279 in this case. You have to calculate the phi function, the Euler function. For that, as you know, we have 3 properties of the Euler function. We can easily calculate the Euler function of a prime number, the Euler function of the product of two numbers if they have a greatest common divisor of 1, and we can calculate the phi of a power of a prime number. Well, in this case we have to know what kind of number 279 is. I can quite easily see that's not a prime number, it's a multiple of 3. If we add all these digits, 279, we get 18, which is a multiple of 3, so then the whole number is a multiple of 3. It's not a prime number, but yeah, what combination of numbers is it? Well, we can do that by trying to factorize the value 279, which means find the prime factors. How do we do that? Well, we check if the smallest prime number 2, if that is a divisor of 279. Well, it clearly is not. So then we go to the next prime number 3. Is that a divisor of 279? Well, yes, we already saw that. And if we divide, we get 93. If you find a division like this, you also have to check it, always have to check it again. So you have to check again, is this 93? Is it divisible by 3? Of course you don't have to check 2 again, but you have to check, is there another 3 in it? And yes, there is. We can still divide by 3. And then we get 31. You have to try it again, but in this case we cannot for a third time divide by 3. So then we go to the next prime number, which is 5. Is 31 divisible by 5? No. Next prime number, 7. Is 31 divisible by 7? No. And then actually we can stop. We don't have to go to the next one, 11. Why? Because 7 times 7, the square of 7, is bigger than the value we have left. We have left 31, smaller than 7 square. That means we can stop. Because if we continue, for example, if 11 would be a divisor of 31, then we would have found another divisor already earlier. So we can stop here. That means we can write 27 as 3 times 3 times 31. You can check that easily on your calculator. So 279 itself is not a prime number. 279 itself is not a power of a prime number. It's not like 5 to the power 6, for example. But it's a combination of 3 values. Our property of the Euler function uses 2 values. So the second property says the phi of A times B is phi A times phi B if A and B are coprime. So we have to try to find this A and B. Well, what we could try first is if we take A to be 3 and B to be 3 times 31, so 93. Would that work? I hope you answered that question by no. Why not? Because these two numbers, 3 and 93, they have a greatest common divisor of 3 and not of 1. So that's not okay. You can not split it up in 3 times 93, but we have another option. We can also take these two numbers together to be A, and we can choose this as B. So then we have phi 9 and phi 31. Is that okay? Yes, it is, because 9 and 31 have a greatest common divisor of 1. So the phi of 279 is phi 9 times phi 31. What about phi 9 and phi 3 to the power 2? Well, we have a property for that. This is a power of prime number, so that's the third property. P is 3, K is 2. So if you apply the third property of the phi function, that's P minus 1 times P to the power K minus 1. And yeah, that's simply calculated as 2 times 3, so that's 6. We also have phi 31 to calculate. Well, that's easy. 31 is a prime number, so that's 31 minus 1 is 30. That means that the phi of 279, we saw in the slide before, it's phi 9 times phi 31, so that's 6 times 30 is 180. So the phi of 279 is 180. Now we have to check, is that phi function smaller than our exponent? Our exponent value is 583, which is bigger than the phi number, so that's good. We can use Euler function. And yeah, remember, what does the Euler theorem say? It says, well, 25 to the power phi 279 is the same as 25 to the power 180, because the phi 279 is 180. We calculated that in the previous slide. That's congruent to 1 modulo 279. That's what the Euler theorem tells us. So the last part is important. We know from Euler that 25 to the power 180 is congruent to 1. And yeah, for the same reason, 25 to the power 360 also has to be 1, because 360 is 180 plus 180. And 25 to the power 180 plus 180 is the same as 25 to the power 180 times 25 to the power 180. That's one of the properties of exponentiation mentioned in one of the lectures. We know already that 25 to the power 180 is congruent to 1. We saw that here. And this one is also congruent to 1, so this is actually just 1 times 1, and therefore also congruent to 1. 25 to the power 360 is also congruent to 1. And for the same reason, 25 to the power 540, 3 times 180, is also congruent to 1. And 4 times 180, 5 times 180, they are all congruent to 1. Well, in this case, we have to work with this power 583. We know now that 25 to the power 540 is congruent to 1. So then we can simplify it a lot. 25 to the power 583 is 25 to the power 580 plus 43, of course. That's 25 to the power 540 times 25 to the power 43. Property of exponentiation. This part, we just saw, this part is 1 because 540 is 3 times the phi function. So this is 1, we can just remove it and we will have only this part left. So from an exponent of 583, we now go back to an exponent of 43, which is a lot smaller and a lot easier to handle. That's the reason that we use Euler. The exponents, they get a lot smaller, and therefore we can more easily calculate our value. But yeah, as far as Euler is concerned, that's it. We cannot continue further with Euler. We are now stuck with this power 43. In order to simplify that, we have to go to the modular exponentiation. Well, in order to apply that, as you saw in the slides, we calculate powers of 25. Which powers? Not all of them, but those powers that are a power of 2. So we calculate 25 to the power 1, 25 to the power 2, 25 to the power 4, 25 to the power 8, 25 to the power 16, because 1, 2, 4, 8, 16 are powers of 2, binary powers. Start with this first one, 25 to the power 1, easy, it's 25. Second one, 25 to the power 2, well, that's of course 25 times 25 is 625. Modulo 279, that's congruent to 67. Then we go to 25 to the power 4. 1, 2, 4, 8, 16. So next is 25 to the power 4. That's 67 times 67. Because 25 to the power 4 is 25 to the power 2 times 25 to the power 2. So that's 67 times 67. If you multiply that on the calculator, it's 4489. Modulo 279 is 25. By chance, we have again 25, the value that we started with. It's not always like that, of course. That's by accident now. Next one is 25 to the power 8, which is 25 to the power 4 times 25 to the power 4. So that's 25 times 25. It's 625, and that's again 67, of course. It's the same calculation as here. Next is 25 to the power 16. That's again 25. Next is 25 to the power 32. That's again 67, because it's 2 to the power 16 times 2 to the power 16 is 25 times 25 gives us 67. And again, it's a coincidence that these values are repeating. I give 25, 67, 25, 67, 25, 67. In general, that will not be the case. It's this specific example. What's next? Well, we were stuck with that power 43 at 25 to the power 43. So we now have to write that power 43 in powers of 2. Meaning it's 43, it's 32 plus 8 plus 2 plus 1. These are all powers of 2. 1, 2, 8, 32. That's 43. So 25 to the power 43 is 25 to the power 32 plus 8 plus 2 plus 1. Is 25 to the power 32 times 25 to the power 8 times 25 to the power 2 times 25 to the power 1. Using the previous slide, 25 to the power 32 is 67, 25 to the power 8 by accident is also 67, 25 to the power 2 is also 67, 25 to the power 1 is 25. So we have these values left. Well, we can take a calculator and calculate them. That's 7519075. That's the combination multiplication of these four numbers. Modulo 279, we have 25. That's the answer to the question. We had to calculate this value. Answer is 25. It took us a bit of effort, but not nearly as much as when we had to calculate this whole exponent, 25 to the power 583. It's really, it's too big to handle. But with a few fairly simple steps, we now have to resolve 25. Of course, you want to check if this is right or not. We can use the site Wolfram Alpha for that. It's coming. Here we can enter the same value, 25 to the power 583 modulo 279. Calculating. Well, takes a long time. In the meantime, I will continue with my last remarks, so that the answer is indeed it's 25. My last remark is you can easily make exercises yourself. Just choose 3 numbers, a mantissa here, an exponent, and a modulo value. Mantissa are not too big. The exponent can be a big number, and the modulo also. And then try to solve such a problem. So choose a random value instead of 25, instead of 583, instead of 279. Try to calculate it, and with Wolfram Alpha you can always check your answer. And maybe you should start with values that are not too big, but yeah, it should work also for bigger numbers. Okay, that's it. Thank you for your attention.